Welcome back. So you have started watching videos on support vector machine, and today we are going to discuss about how the classification problem can be formulated or modeled in a constrained quadratic optimization problem. And then, of course, how to solve that problem. Okay. In my earlier lecture, of course, I told that how it is different from all other classifier and what is the uniqueness and who discovered it and all kind of things we discussed. So those who are wants to know introductory things, you can just refer to my earlier videos. So stay tuned. So this is actually um, two classes. Samples, say this is belongs to negative class and this belongs to positive class. So it is a again discriminatory model, means you need a label data to classify, and here the say y this is the level, or this is I is the sample. Okay, so here unlike the architecture is like this. Okay, two classes are denoted as -1. So negative class is -1, positive class is +1. Okay. Earlier you have seen it was normally 0 and 1. 0 belongs to one class, 0 denoted one class, 1 denoted another class. But here this is the architecture actually. So here we can see that we have some negative class samples belonging to the negative class, samples belonging to the positive class. Okay, and we are trying to what we are trying to do first, trying to make a decision rule. How we consider any arbitrary point with position vector v. Okay, and we are trying to formulate a decision rule, and we have defined w as a vector perpendicular to the garter. Okay, and this is so these are my support vectors. Say somehow I know this. Okay, and these are my garters. Okay, and this is perpendicular to the garter, and also of course therefore perpendicular to the decision boundary or decision line. Okay, so what I am trying to do, I am trying to take the arbitrary vectors projection on this direction. Okay, and I am making a decision rule that is, say k is any constant, arbitrary constant, say equals to, I am putting the value minus b. Why minus b? Mathematical convenience, you will see. Okay, so what is this actually? So if v dot w greater than some value, some constant, then it belongs to, say, one class. And then if less than k, it belongs to another class. Let us refine a little bit this. Okay. Plus b greater than equal to 0, then the sample belongs to positive class. Okay. And if plus b less than 0, then the sample belongs to a negative class. So these are my decision rule, which I have formulated very intuitively. Okay. So this is W. Remember, please, that is a support vector machine parameter, is not weight parameter like in other classifiers. The problem is we have formulated the decision rule only. We do not know yet that which W um, or B to be chosen. Okay, and also we do not know what are the constraints to be fixed. Okay, so let us try to do that. Try to develop constraint. Okay, isn't it? Without constraint, this decision rule is not going to help us, because we need to put constraint that what you see B. So this is actually, um, the decision surface will, the decision boundary will depend on B, on W, okay, and B actually is some uh, bias or something like that, which we'll know. And if W is this much, then the decision gutter will be here and decision boundary will be here. If W is too big, say W is this, so W actually is determining where. It's just like gutter is just like a structure you can imagine, and this is the handle of the umbrella like thing, is a solid rod. So if it is small, so this will be here. It is big, so this gutter will go there, and that's how decision boundary will be fixed. So we need to do that. Actually, we need to get values, we need to formulate constraint. Okay, uh, for example, take a positive sample. Say everything is vector, that's why I'm putting this positive sample with the vector sign. So then if it is positive, it belongs to positive class, then what? Dot plus B greater than equal to 1, and then W plus B must be greater than 1 if the gutter size is 2. Okay, so this is, let us call 1, and this is 2. Then if take a negative sample, then -1. So do you remember we have structurally what we decide, that this will be belonging to -1 or +1, right? So my negative class is -1, positive class is +1, and there is a motive behind, you will see, behind denoting my class like this and not like this. Okay, it will be visible right now. So now introduce another. Now I am. So we have now some constraint, right? Okay. So if it is greater than or equal to 1, suppose we know now, somehow we know W value and B value we know, and then any sample I plug in, make the dot product, and I see whether it is greater than 1. Then I infer, yes, it belongs to positive class, or it belongs to, if it is less than -1, it belongs to negative class. Okay. So let us try to denote. Okay. So how to combine 2 and 3? You see, just that this equals to +1 for positive class equal to -1 for negative class. So I am introducing a parameter wi as I an sample, right, plus b -1 greater than equal to 0. Okay. So for any sample on the cutter, I can just get a constraint like this. You see, wonderful. Okay, so for any sample, so this is, say, let us call it 4. This is valid for any sample, for any sample on the gutter, isn't it? So any sample on the gutter, that is, we are calling, they are incidentally called support vector. So what we have done, we have just have a decision boundary. Then very intuitively also, we have defined our structure of the class representation, right? And then very intuitively we have got constraint, and using this we have just clubbed 2 and 3 for mathematical convenience, and we have got a constraint like this. Okay. So now, what is the, you see, now if this vector is known to me, so here everything is vector. That's why it's called subvector. Okay. These are the samples. Okay. And say A. I'm just naming them so that B. And this is my, say, um, W. Okay. So what is the width of the gutter? We are trying to figure out. Okay. Geometrically, you see, AB, this is the width of the gutter. Okay, but this is not perpendicular, so we'll have to take a projection in what direction? Perpendicular direction, because otherwise this could be also width, this could be also width. Width doesn't mean everything, right? Width will be the perpendicular distance between this. And how to find it? I will take a projection of this vector. So I have taken any sample. So this is another sample belonging, support vector belongs to positive class, support vector belongs to negative class. So this is my vector. Okay. So I got the distance between them. Okay. And then I am trying to figure out, taking its projection to get the width. Okay, like this. So AB dot W is the width of the gutter. Okay, isn't it? Okay. So in terms of my support vectors, fine. This is my actually width of the gutter. You are all with me? Convinced? AB, AB is what? Um, this is very simple. OA plus AB equals to OB. Okay. So AB equals to OB minus OA. So this is now dot w, and I am making unit vector. So this is my direction. Making a unit vector in that direction and projecting AB on that unit vector direction to get the width of the gutter. So OB, actually you can see OB is uh, AB equals to OB minus V. So we are getting from now for positive sample, what we can write is plus B minus 1 equal to 0. That gives you equals to 1 minus B. For negative sample, uh, 0. So that indicates minus W equal to 1 plus B. So now from 5, this is algebra, nothing else. Okay, the width of the gutter equals to how much? You tell me. Minus this. I'm putting minus this equals to 1 plus B plus this equals to 1 minus B. So, uh, so, the expression 5 becomes 2 divided by, okay, width of the gutter equals to this. Now, we are in a position to formulate our objective function, right? What is the objective function? The width of the gutter is to be maximum. So our objective is maximize 2 by. Okay. That means minimize this. That means minimize now. This is my objective function subject to what are the constraints? Subject to y sub I w dot s sub I plus b minus 1 equal to 0, and I'll have to minimize over what? So over this parameter, this. So this is my optimization problem. You see. Now, you see this width of the gutter was 2 by W. So why we did minimization problem? We took dual. Okay, they are the same. Okay. You see why we took this? Because mathematical convenience. What we are wanting to do? We are wanting to formulate this classification problem as a quadratic optimization problem. That's why we could have done half W, but no, W squared, because it's all the same, right? And we could have maximized this, but then we could not take the help of quadratic optimization problem solver. So maximization of 2 by W, we took the dual of it, okay, that we do for mathematical components many times, and that becomes half W, and that means my optimization problem now becomes uh, minimize half W squared over parameter W, okay, subject to the constraint y sub I. So this is a constant I have written. So now perfectly it becomes a, there is a constraint, there is an objective function. So constraint quadratic optimization problem. Formulation of that maximum Gatter which you are wanting is nothing but this is minimize this subject to this. Okay. Now once we have done that, that's the intelligence, that's the elegance of support vector machine. Once we have done that, we very well know how to solve this. And you know how to solve this? Solve this optimization we use which? Lagrangian multiplier method. So this is very, very important. Perhaps you know what we do actually. You see, this is very standard one. Okay, this is if this kind of objective function optimization problem is there, we use Lagrangian multiplier method to solve this optimization problem. And what is that Lagrangian multiplier method? You can brush up, but here this is very standard theory. But here I will just try to brief you that we introduce. Uh, so this is our 6 problem mark 6. So we introduce a Lagrangian multiplier, say in the form of alpha, with every sample. Okay, this is my constraint. So what I do, I multiply constraint by Lagrangian multiplier, and then first of all I try to formulate a Lagrangian function. How? Just by, this is my objective function, and I incorporate the constraint with the help of Lagrangian multiplier, say alpha I, then y sub I dot minus 1, and let us call it let us call it. So what we have done, we have formulated Lagrangian function L. How? Just we have copied the objective function here, and since this is 0, alpha times of this expression actually has not changed anything, right? But it has done a great thing, which we are going to. So this is Lagrangian multiplier method. So you multiply constraint with Lagrangian multiplier and incorporate the same thing to your Lagrangian function. So this is called Lagrangian function. Isn't it? So you can just study the theory behind it, or you can just think about it that here is an objective function. I have multiplied this constraint with alpha I, and since the constant equal to 0, so we have not done anything but it is an objective function only. But in tactfully, I have incorporated in my objective function all the constraint, and then what we'll do? Definitely, you know that I need what I am looking for. I am looking for the values of parameter feature W and B. Samples are giving to me. Okay, class levels are giving to me. Okay, so I need to figure out the parameters W and B. And how can you do that? If you have an expression, just differentiate that once with respect to W, make it 0, and you will get some equation. You make it 0, you will get some condition, and that's actually the expression will start dancing. And in doing this, we will crank out everything we require for solving this support vector machine problem. So we are going to take from here, and we'll show you how actually we can solve the problem, and then we'll solve one hand problem. Small problem we'll take so that we can solve by hand, so that you can digest what is happening. But I think you have understood so far. Theory is very simple, very intuitive idea, and once you have formulated it in the form of um, quadratic optimization problem, then use standard Lagrangian multiplier method to solve it. So that's the great idea. And since it has now started giving a result, we will uh, um, discuss more deeper, go deeper and see how the results can be obtained. Okay. So stay tuned, and in the next class, we're going to take over from here. So have a nice day. Stay safe. Bye bye.